The Sun, the center of the universe. The Earth, just an ordinary planet orbiting the Sun, like all the other planets. With this bold insight, the 16th century astronomer Nicolaus Copernicus ushered in a fundamentally new view of our solar system. It was a scientific revolution. But it was not until half a century later that the German mathematician Johannes Kepler, using observational data provided by the Danish astronomer Tycho Brahe, succeeded in drawing an exact picture of the solar system. Since time immemorial, man has taken an interest in the heavenly bodies and sought to understand the rules by which they moved. It was soon noticed that most stars seemed not to move relative to each other. These were known as fixed stars. Where they formed conspicuous patterns in the sky, they were grouped together in constellations. Mythological significance was attached to these groupings. In the course of a night, the stars revolve in a circle around the pole star, or at least they seem to. For today we know that it is really the Earth that moves. Greek philosophers regarded the circle as the perfect form, and at the center of this circle, they were sure, was the Earth immobile. But it was also noticed that some stars did move relative to the others. These were called planets, after the Greek word for wanderers. Curiously, sometimes some of these planets seemed to be moving backwards. Mars, for example, when observed from Earth, moves slowly from west to east for months, then seems to come to a halt and move east to west for a few weeks before continuing in its original direction. In order to keep Mars conceptually on a circular orbit, which they regarded as ideal, Greek astronomers hit on the idea that these planets might move on circles within circles, known to mathematicians as epicycles. In around 100 AD, the astronomer Claudius Ptolemy, who lived in Alexandria in Egypt, summarized the work of the Greek astronomers before him into a system that was to hold sway for more than 1,000 years. In this Ptolemaic system, the Earth is at the center of everything. All the celestial bodies revolve around it. Ptolemy assumed a total of 70 circular movements, all going on at the same time independently of each other. This system allowed him to predict the positions of the planets with reasonable accuracy. During the Middle Ages, the Arabs brought back to Europe the knowledge which they had inherited from the Greeks. From then on, the Ptolemaic system determined the world view of the Catholic Church. But could God's creation not be explained rather more simply? This question occupied the Polish scholar Nicolaus Copernicus in the early 16th century. After years of calculations, he came to the conclusion that all the planets moved at uniform speeds in orbits around not the Earth, but the Sun, which he thought was at the center of all things. But he had no way of proving this. The Catholic Church rejected the Copernican system and placed his writings on the index of banned books. The German reformer Martin Luther didn't think much of the new theory either. For him, Copernicus was just a fool. Even so, Copernicus had his supporters. One of them, a teacher at the Protestant University of Tübingen, was the astronomer Michael Messlin. He had a student named Johannes Kepler. Johannes Kepler was born on the 27th of December 1571 in Weil, a small town in southern Germany. Although his parents were poor, he was able to attend school. The Protestant state of Württemberg provided all of its children with 3 years of free education. It was soon realized that young Johannes was a bright boy, and he was sent off to Tübingen University with excellent school grades. There, Michael Messlin fired his interest in mathematics, astronomy, and the Copernican system. Young Kepler had wanted to become a pastor, but now he felt himself called upon to provide a proof of Copernicus's theories. It was also Messlin who persuaded the 23-year-old Kepler to go to the Protestant Austrian city of Graz, where they needed not only a good mathematician, but a Protestant mathematician. One of Kepler's responsibilities in Graz, alongside mathematics, was to produce an annual calendar and horoscope. But Kepler was not interested in putting the exploration of the heavens to such banal use as making earthly predictions. In 1596, he published his Mysterium Cosmographicum, The Secret of the Universe, in which he defended the Copernican system, but still he had no proof. One man who thought he did have proof was the Danish astronomer Tycho Brahe. Not of the Copernican system, but of the Tychonic system, named after him. This still had the Earth in the center, but he thought it was orbited only by the Sun and the Moon. All the other planets, in the spirit of Copernicus, went round the Sun. Brahe found that his model would precisely explain the planetary movements as seen from the Earth, except for that of Mars, which still showed irregularities. Brahe had at his disposal the best observatory of the age. His patron, King Frederick II of Denmark, had even given him the use of the island of Fyn for just this purpose. Here, Brahe was able to observe the night sky undisturbed. His rapidly growing and very accurate database made him famous throughout Europe. But when Frederick died, Brahe's days on Fyn were numbered. The new king, Christian IV, was no longer willing to finance this often domineering astronomer. Brahe left his observatory, island and homeland in disappointment. 2 years later, the man with the golden nose, he had lost his own in a duel, was wandering around Central Europe when he found a new sponsor. He became court astronomer to the Holy Roman Emperor Rudolf II in Prague. Some 30 kilometers from the city, in Benátky Castle, Brahe set up a new observatory, with the best instruments money could buy. What he lacked was a capable assistant who could derive the definitive proof of the Tychonic system from his extensive database. Kepler applied for the post and got it. He had already had to leave Graz after the city was reoccupied by Austrian Catholics. Any Protestants had either to return to the old faith or clear out. In the summer of 1600, Kepler arrived in Benátky Castle and took up his employment with Brahe. Relations between the two men were tense from the outset. Brahe regarded Kepler as a mere assistant, someone to whom he could delegate mathematical tasks. A human computer, in other words. Kepler, though, was a sensitive man, and Brahe's domineering manner irritated him. Quite apart from that, he thought the Tychonic system was plain wrong, but he kept his mouth shut on that score. He had come to Prague to make use of Brahe's observational data, the best in existence, and he wanted to keep his job. Then, just a year after his arrival, things suddenly changed with the unexpected death of Tycho Brahe. On his deathbed, Tycho had implored his assistant to fight for the final recognition of the Tychonic system, but Kepler was unable and unwilling to keep this promise. Now, as Brahe's successor at the court of Emperor Rudolf II, he found himself in possession of papers which would finally ditch any view of the universe, including the Tychonic, which placed the Earth at the center. Kepler looked particularly hard at Mars, whose orbit Brahe had measured. He sought to understand the planet's path in Copernican terms. After 4 years of hard work, he realized this wasn't possible. There was only one conclusion. Something in Copernicus's theory was wrong. As a result, Kepler came to formulate his first law, which dispensed with a 2,000-year-old tradition. The planetary orbits were not circles, but ellipses, with the Sun at one focus. Kepler also slaughtered another sacred cow, namely the idea that the planets moved at constant speeds. In reality, they move faster when nearer the Sun than when further away. In his second law, he showed, again using Brahe's data, that an imaginary line between a planet and the Sun sweeps out equal areas in equal times. Kepler published both laws in his work Astronomia Nova, or New Astronomy, in which he developed a concept of planetary movement that had nothing to do with the ideas of the Church. Planets, he thought, were no longer moved by angels, but by a force emanating from the sun. But what this force was, he couldn't say. Kepler's book aroused little attention. Even the famous Italian astronomer Galileo Galilei kept his silence. Kepler was very much a loner with his ideas, but he worked on tirelessly. Then in 1618 everything changed. A bitter internal conflict between Protestants and Catholics in Bohemia quickly escalated into the 30 Years' War. A year later, Kepler published his Harmonices Mundi, or Harmony of the World, whose title summarizes its content. He detected a harmony in the universe. In it, he added a third law to his other two. This third law was perhaps the most remarkable. It describes a characteristic constant which can be calculated from the orbital period of a planet and the semi-major axis of its elliptical orbit. Kepler's third law is valid for all heavenly bodies orbiting a common central body. The Moon shares the same constant, for example, with artificial satellites in Earth orbit. The same is true, with a different constant, of all the planets, asteroids and comets orbiting the Sun. Kepler was now certain he was beginning to understand God's plan of creation, but he did not fall prey to the illusion that his Harmony of the World would be immediately understood. In his preface he wrote,
"My book may have to wait 100 years for a reader, for God himself had to wait 6,000 years for someone who could penetrate his work."
In fact, it took about 50 years before this reader was found. The English scientist Isaac Newton. Kepler's third law forms the basis of the law of gravity that Newton published in 1687 in his monumental work, the Principia Mathematica. In it, Newton describes a universal force of attraction which is a property of any body possessing mass. This force explains the movements of the stars, the planets and their moons. Newton was a legend in his lifetime and received a knighthood for his scientific achievement. Kepler, by contrast, was denied fame and social success. Worse still, as a Protestant, he was forced to leave what was now Catholic Prague. But where could he go? The 30 Years' War was raging throughout Central Europe. The general of the Imperial Catholic forces, Wallenstein, offered Kepler a post in the relative security of Sagan in Silesia. But Wallenstein had no interest in astronomy. All he wanted to know was whether the stars were favorable for his military plans. Once again, Kepler was forced to earn his living from horoscopes. But Wallenstein didn't even pay on time, so Kepler got into serious difficulties. He went to Regensburg in the hope of calling in some old debts of his own. There he fell ill and died on the 15th of November 1630. He was buried in the Protestant cemetery outside the city. 3 years later, the site was laid waste in the confusion of the war. Kepler's work made the Copernican worldview unassailable. Working entirely alone, he succeeded in using Tycho Brahe's observational data to correctly interpret the movements of the planets. His achievement went unrecognized in his lifetime, but our modern view of the universe is still based on his insights.